Hey guys, so now we're going to go ahead and do an example of curve sketching using all its steps using a polynomial function. So let's go ahead and get started. So whenever we do curve sketching, right, we put everything together. And by everything, I just mean all the steps in my checkbox that start with domain and ends in the final sketch of the graph. So starting off, we're going to do the domain of this polynomial function. And the domain of a polynomial function is actually real easy because it is always the same. The domain of a polynomial function is always going to be from negative infinity to positive infinity. Or, in words, we can always say that it's all real numbers. Alright? That's what we're talking about, the domain of a polynomial function. And if you guys have, for some reason, lost your touch on domain, maybe intercepts, symmetry, or asymptotes, those are all parts of pre-calculus, which I did cover in previous videos. So you guys can go back and make sure you guys can kill those topics before we jump on and do curve sketching, because if not, you may get a little lost, and I don't want it to happen. Because I'm going to be moving pretty quickly through these steps, assuming that you guys already know this. It'll be just kind of like a review. Alright? So the domain of this polynomial function is just going to be all real numbers because it's always all real numbers, right? We learned that in domain. There's no restrictions when it comes to polynomials. They're good functions. And now when we go into in part B, we're going to talk about the intercepts. And the intercepts, we're always going to start off with the y-intercept when it comes to polynomials because it's easier, right? We're doing the x and y-intercepts. We're doing both. But y-intercepts are going to be easier to compute. And how do we find a y-intercept? We make x equal to 0. So let's go ahead and do that. Let's go ahead and find f of 0, in which we're making every x in f of x 0. So it's going to be 0. It's going to be 0 to the 4th power minus 13, 0 squared, plus 36. Alright? So now, let's go ahead and do that. When we compute that, you guys will see that you guys get 36 for the number. All the terms that have an x in it are just going to cancel. And then we go ahead and just write it down our coordinate, which is going to be 0 for the x. We made the x equal to 0. And we got 36 for the y. So now we're ready to jump on and do the x-intercepts. X-intercepts. Which we find the x-intercepts by making the y equal to 0. Or the f of x equal to 0. And in this case, what we do is we just make the f of x equal to 0, this right here, or we set the whole equation equal to 0. So we're going to have x to the 4th minus 13 x squared plus 36 equal to 0, right? And we have a polynomial, so when we said polynomial is equal to 0, the natural thing to do is just to factor. So we go ahead and factor this, looking for two numbers that multiply to 36, but add up to 13. And that's going to be 9 and 4. There's also a little twist here from factoring. We have an x to the 4th, right? So when we have an x to the 4th, we can't just do x and x. We need to have an x squared and an x squared here. X squared and x squared here to make sure that we get an x to the 4th. Just look out for that. Those are factoring tricks. And then there's going to be minus and minus. And now when we get here, we can further factor this, right? We can further factor these difference of squares that we have here, x squared minus 4 and x squared minus 9. We can further factor them into x minus 2 and x plus 2. And then we're also going to factor the other one into x minus 3 and x plus 3. And what we do now is we go ahead and set them all equal to 0. So x minus 2 equal to 0 just gives me x equal to 2. X plus 2 equal to 0 just gives me x equal to negative 2. X minus 3 equal to 0 just gives me x equal to 3. And then x plus 3 equal to 0 just gives me x equal to negative 3. So a lot of work there that we have to do, but now we're done. And now we're just going to write our coordinates, which are going to be 2, 0 for the first one, negative 2, 0 for the other one, 3, 0, and then negative 3, 0. So now we have a total of 5 points that we know about our function, right? That we have gotten from the intercepts. Plus we know its domain that has no restrictions. So let's move on to part C, in which we talk about symmetry. Right? So in part C we talk about symmetry. And to start off symmetry, we always just compute f of negative x, right? So let's go ahead and do that. We're going to have x to the fourth minus 13 x squared plus 36. So we're just going to put a negative x right in there. You guys are pros at this. We did a lot of examples on symmetry. And now the final answer is going to be a negative x to the fourth. It's just going to give me a positive x to the fourth because I'm raising it to an even power. And whenever I raise it to an even power, it's just going to be a positive answer. I'm going to have my minus 13 here. And then I'm going to have my negative x to the raised to the second, which is also going to give me a positive answer of x squared. And then plus 36. And now we're going to compare it to my f of x, which is x to the fourth minus 13 x squared plus 36. And if we notice, these two are actually identical, right? These two are the same, which we can say that f of negative x is equal to f of x. And when that happens, we have y-axis symmetry in which our function is even. So we have y-axis symmetry, or we have an even function. Okay? So now let's go ahead and do part D, in which we have to compute the asymptotes. And we're not only concerned with the asymptotes in this part, but we're also concerned with the end behavior. So let's go ahead and write that up there. So you guys can remember that when we talk about the asymptotes, we also care about the end behavior. I'm going to go with BEH to abbreviate it. So when I do that, I'm going to first start off with the asymptotes, with the vertical asymptote. We always said the vertical asymptote is the easiest to compute, so we start off with that. But the vertical asymptote in this case of a polynomial never exists. So we have no vertical asymptote because we're dealing with a polynomial. So that made it easy to just get rid of one step that we would have to deal with if we weren't dealing with a polynomial. So now we're going to move on to horizontal asymptotes, but not just the horizontal asymptote at its normal definition, which is the limit as x approaches infinity, which would be a horizontal asymptote. We're also going to care about the end behavior. We're going to mix the end behavior and the horizontal asymptote all at once, in which we're just going to compute limits, right? So for that part, we're just going to be computing limits. The limit as x approaches infinity of f of x, and the limit as x approaches negative infinity of f of x, right? But when we're talking about f of x, we're only going to care, when it comes to polynomials, we're only going to care about the leading term. And that leading term in this case is going to be x to the fourth, right? So we're only really caring about inputting infinity or negative infinity into x to the fourth, which means that we're going to have blank to the fourth, right? In this case, we're going to have positive infinity to the fourth. And that is going to lead us to positive infinity, because infinity to the fourth power is just infinity. And then when we're inputting negative infinity into x to the fourth, that is just going to give us, as well, it's going to give us positive infinity. All right? So now, steps A through D, you guys actually notice, when we're talking about domain, intercept, symmetry, and asymptotes, all of this is actually pre-calc. It's pre-calculus. Right? It's pre-calculus. And we actually do the calculus here in these steps to get to our final outcome that we are actually going to do, just sketching the graph. So all those pre-calc topics, like I said, are in previous videos that you guys can go back to. And now we're going to include the new stuff that we just learned about max and mins, and also intervals of increase and decrease. So let's go ahead and do that. Let's go ahead and see the local max and the min. And this all constitutes to the first derivative test, right? So the first derivative test starts off with taking the derivative. So once again, these two steps right here, are going to be constituting with the first derivative test. And by doing that, I mean that I need to take the first derivative. So let me go ahead and do that. And I'm going to do that in blue. Which is going to be 4x cubed minus 26x plus 36. And then the second step of the first derivative test is going to be to set the first derivative equal to 0, right? And then I'm going to set 4x cubed minus 26. Oops, there was a 36 there in the derivative that just snuck in there. That shouldn't have happened. Equal to 0, right? So once I have this, I'm going to go ahead and factor out what I can, which is going to be I can take out a 2x from both of these. And I'm going to get here a 2x squared minus a 13 left. Now I'm going to set each term equal to 0. So I'm looking now for my critical numbers, right? I'm setting my first derivative equal to 0 to look for my critical numbers, which we learned in the videos about the first derivative test. This is going to give me 0. And this is going to be a little longer, more painful, but it's going to give me 13 over 2. And then we're going to take the square root, and then we get plus or minus the square root of 13 over 2, which gives us a number about 2.5. Okay? It gives us a number of about 2.5. Let's kind of put like the correct notation, which is like some wiggly things, like it means approximating 2.5. And now, after we find our critical numbers, we need to do our number line, so we can see where we have a local max and a min with a change from positive to negative or negative to positive. So let's go ahead and do a number line here in green, okay, in which we're going to put 0 in the middle because we need to include this guy, and then we're going to put the negative 2.5 and the positive 2.5. I'm actually going to put 13 over 2 to be specific, and 13 over 2 here to be specific, right? So I have a negative number to the left of 0, and I have a positive number to the right of 0. And I know this is taking a while, trust me. I know we've been beating a dead horse here by having to do all this curve sketching stuff, but we need to get through it so we can get to our final step of sketching the graph. So just stay in there with me. So here we have that we need to now find our testing numbers, right? So a number less than 2.5, I'm going to go with just negative 3, right? A number between 0 and 2.5, I'm going to go with negative 1. Seems like an easy number to go with. Between 0 and 2.5, it's going to be 1. And then after 2.5, it's going to be 3. Alright? I'm just going to pick those numbers. They're easy. You're going to have to pick other numbers. You're going to get the same answer anyway. And it's not a big deal. And once again, let's make sure we label our number line because this is the number line of f prime of x. So that's the number line of the first derivative, which we use to find local max and local mins along with intervals of increase and decrease. Okay, so now we're going to go ahead and input these numbers, right? So if I input negative 3 into my derivative, which you can be inputting it into whatever you want, right? You can be inputting it into this guy right here, or you can put it into this guy right here, or whatever you like to input it into. As long as it's a derivative, you're going to get the same answer, right? So I'm going to go ahead and input it into this guy right here, right? And you guys are allowed to do it too, into the other one, it's fine. If I input a negative 3, I am going to get a negative number. And you guys are allowed to check that on your own, right? So if I input a negative 3 into my derivative, I get a negative number. Now if I input a negative 1, I'm going to get a positive number. A positive number. If I input a 1, I'm going to get a negative number. And if I input a 3, I'm going to get a positive number. And I like inputting it into the one that I boxed out because I get to be like, okay, let's say I'm inputting 3, right? I'm going to be like 2 times 3 is a positive. So the first term right here gives me a positive. What do I get in the second term? Okay, the second term, 2x squared minus 13, that's positive. So positive times positive gives me positive. I deal with smaller numbers than if I were to use the original equation. So that's why I like using the factored version. But it's up to you guys. That takes a little long time, inputting, checking, make sure you're right. But it's what we got to do. So now that we have all these changing in signs, we can see different things, right? We can see that at the negative square root of 13 over 2, we go from negative to positive, which if we draw that out, we're going from decreasing to increasing. We have a min, right? And then here, for the 0, we're going from positive to negative, so we're going to have a max. And then when we go back up, we go back up, we're going to have a min, right? So we actually have 2 local mins and 1 local max that we can talk about, right? So I'm going to go ahead and say that right here. I'm going to go ahead and put that right here. So I'm going to have a local max first. I will have 1 local max, and that's at x equal to 0, because I go from positive to negative. Or you can just use a little trick where you go decreasing, increasing, decreasing, increasing. And then we have a local min at x equal to, well, we have 2 of them, right? We have them at plus square root of 3 over 2, and then we also have them at minus square root of 3 over 2. So we have them at those 2 points. And then we're also going to kill part f, because here we're talking about part e and part f together, which we could talk about the intervals of increase and decrease, right? In the intervals of increase and decrease, we're going to put them right here. I know we're like real crammed on time, but you guys have like extra paper you guys can just bring around or write or whatever. I'm going to try to keep all the information in this box so you guys stay focused in this one box. So now, when I talk about the increase or decrease interval, I look for increasing, I look for my derivatives positive. That's going to be right here and right here. So my derivative is positive there. So those are my intervals of increase, right? Which are going to be from negative square root of 3 over 2, comma, to 0. And union, I'm also going to talk about the other positive side, which is going to be the positive square root of 3 over 2 all the way to infinity, right? So those are my 2 intervals where I'm increasing or where my derivative is positive. And then also where I'm decreasing, I'm going to talk about where my derivative is negative, which is going to be right here or right here, right? So those 2 intervals are going to be from negative infinity to negative square root of 13 over 2, and also from 0 to the positive 13 over 2, to the square root of positive 13 over 2. And we're going to close that interval in there. And I know there's a lot of information to fit into one box, because we pretty much did the first derivative test in one little tiny box. But we did it. Now we're going to move on to part G, which is concavity and inflection points. And this talks about the second derivative test, right? The STD. Funny name there. But let's go ahead and talk about the concavity and points of inflection, which we start off by taking the second derivative, right? So I already have my first derivative here in my first derivative test. So I just go ahead and take the derivative of that to jump on. I don't need to do a double derivative. I just pick my derivative from that one. And then I'm going to get 12x squared minus 26. Nobody snuck up on us this time. I like that 36 I wanted to be in the first derivative. And I'm going to go ahead and set it equal to 0 and do the same old dance, right? I'm going to try to make it a little quicker. So I'm going to have 12x squared minus 26 equal to 0. So now we're just solving for x. 12x squared equal to 26. Now I have to divide by 12. 26 over 12. That's going to be annoying. That's going to be, if I divide 26 by 2, I get 13. If I divide 12 by 2, I get 6. So I reduced it. So then I get, now I square root both sides, and I get that x is equal to the square root of plus or minus 13 over 6. Which that is about, I would say, about 1.5. So let's put the little estimation. So we're proper in our notation, and we got that we actually have 2 points here that we're going to care about. We have 2 possible points of inflection. Remember that not every 0 of the second derivative is automatically a point of inflection. We need to test them so we can check if it's a point of inflection or not. And how do we test them? We go straight into our number line, and here we're just going to have this negative square root of 13 over 6 and this positive square root of 13 over 6. So after I do that, I'm going to go ahead and label my derivative line, because I can see that I have 2 number lines, but one belongs to the first derivative and the other belongs to the second derivative. So I'm very careful when it comes to that. And then now I'm going to go ahead and pick my middle numbers, right? So my middle numbers. So a number less than square root of 13 over 6, that's going to be, I don't know, well, we're looking at negative 1.5. So I'm going to go with 2. With negative 2. That is my easiest and closest number. A number between the negative square root and the positive square root, well, an easy number between any negative and positive number is going to be 0. It's going to be really easy to compute, and we're going to like that number. And now, we're going to talk about a number greater than 1.5, which again is just going to be the positive 2 in this case, right? It's going to be the positive 2. So let's go ahead and input them. So now if we input a negative 2 into our second derivative, which we only really have one option here. If I were to input it into here, I would get a positive number. And if I were to input it into my 0, if I were to input 0, I would get a negative number. That's kind of the easier one to look at. And then if I were to input a positive number, a positive 2, I would get a positive number, right? So since now I can talk about my zeros of the second derivative, and I can tell you if it's a point of inflection or not. Because I can look at my number and then be like, okay, I see that before the square root of 13 over 6, before the negative square root of 13 over 6, it was positive, and then after it was negative. Hey, there was a change there in concavity, there was a change in signs. Therefore, I have a point of inflection. But before we answer that, we need to answer our concavity intervals, right? So I need to give you guys the intervals where it's concave up and where it's concave down. Well, that's kind of easy part, because we just gotta look for where it's positive for concave up, which is going to be right here. Right here is positive. So those are intervals for concave up. So it's going to be from negative infinity to negative square root of 13 over 6. And also, we're going to put a union here, a union there, and from the square root of 13 over 6, let's make sure we have a little more space here, the square root of 13 over 6 to infinity, right? Those are the intervals where we have a positive concavity. And then now where it has a negative concavity or concave down, it's going to be right here just between the two square roots. So it's concave down between the two square roots. So we actually have a lot to say about these things, right? And this almost looks wrong in the sense that I just have like the square root over the 13. It's the whole thing that we have a square root of. Okay? So now that we talked about its concavity, where it's concave down and concave up, we can go ahead and talk about its points of inflection, which is actually the easiest part. Because we just look, okay, cool. Do we have a point of inflection there at the negative square root of 13 over 2? Yes, because it changes from positive to negative. Boom, done. Now let's go to the other one. It's positive square root of 13 over 6. Hey, it's negative before, it's positive after. There's a change in sign. So hey, we have 2 points of inflection. So we're going to go point of inflection, POI. You guys will see this quite often. At x equal to plus or minus square root of 13 over 6, right? So in this case, both zeros of our second derivative were points of inflection. And now it's game time, right? Now it's game time because now we actually need to put everything together. And we'll just start off by going down the list. Our domain, cool. Our domain is all real numbers. We have no restrictions. We're good. Our intercepts, we have a lot of points to plot here. So the first point is going to be 0 and positive 36. And I'm going to go ahead and do this with green. Seems like the color I want to use. I'm going to go like up here, just 0, 36, up there. Cool. It doesn't have to be specifically perfect. We just got to like kind of just sketch it out. And then we're going to have to plot 2, 0, and 3, 0. And then negative 2, 0. We'll give myself a little more space there. I'm even going to make this graph a little weird looking so I can make it easier for me to graph this, right? So I'm going to make my dots red. I have just finished graphing my intercepts. I'm done with my intercepts. You guys can still see. And now I'm going to talk about my symmetry. Well, I have points to the left and to the right of the y-axis. So I see my y-axis symmetry there on my intercepts. And then we're going to talk about its end behavior. Okay. Its end behavior says that it goes to positive infinity, right? So all we know about the end behavior is that the right side somehow, and the left side, the left end behavior goes to, which is right here, this is the left end behavior, goes to positive infinity. And here the right end behavior also goes to positive infinity. So we're just going to say it looks something like this. Right? We don't really know where exactly. We're just going to leave those two lines like that. Boom. Now we're going to go ahead and talk about the local max and mins, right? So before we talk about the local max and mins, we're going to talk about the intervals of increasing and decreasing, right? So we're saying that we actually should plot these points, right? Or zeros or critical numbers, which is negative square root of 13 over 2 or negative 2.5. So negative 2.5 is actually going to be somewhere in here. So this is actually where I'm going to put. So this point right here is like my blue line is my negative 2.5, and my positive 2.5 is going to have that. And then I'm going to say that your function is decreasing, right? Starting from negative infinity over here. I'll show you guys what I'm talking about right here. I'm going to start decreasing up to my point of negative 2.5. So I'm decreasing up to this point, right? But in order to get to my blue point, I actually need to cross the x-axis. Because if I'm going to decrease all the way up to this point, the only way that I can do that is by crossing my x-intercept and crossing the x-axis, right? So I'm going to cross my x-intercept and cross the x-axis. Then I tell you that after that critical number, after the negative square root of 13 over 2, I'm going to increase up to 0. Okay, I'm going to increase up to 0. So I'm increasing. I pass my x-intercept, very important. And then I'm going all the way up to x equal to 0. Well, I have to touch over here, so there's a one-way street from the bottom there all the way to my y-intercept. And then after 0, my graph tells me that I am decreasing. I am decreasing all the way up to 13 over 2, right? And that it's all the way up to the up to the blue line, which is somewhere down here because I need to cross through my x-intercept, right? And then after that critical number, I am to go ahead and increase all the way up to infinity. So after I hit up this point, I just go ahead and just boom, I just increase, right? So this is like a very rough sketch, right? Because we know that our polynomials don't look this rough. They look a little smoother, right? And that's when we bring in the concavity part. The concavity is going to give you a nice little smiley face, a little sad face, and that is the second part. So we're going to go ahead and sketch that now. So now we're saying that from negative infinity, we always start off by following the number line, because the number line tells us from left to right how we're going to draw this. So from negative infinity to negative square root of 13 over 6, which is about 1.5. So now let's identify where 1.5 is. So 1.5 is actually going to be, I'm going to say that this is negative 1.5 is all the way down here. And then positive 1.5 is all the way down here, or in the x values, right? So I'm just going to draw a straight line up so you guys can see that we're going to change concavity at those points because we're going from concave up to concave down. So now we're going to redraw our whole line, but I want to do it in another color. So I'm probably going to go with blue. So you guys can see that from the left point of this graph, from the left point of this line, we're going to have a concave up. So I'm going to make this a lot smoother. So you guys see how I made my line a lot smoother, and it's concave up because it looks like a happy face. And I have not violated anything. I am just doing the concavity part. And now between the two black lines, between the negative and the positive square roots, I am going to go ahead and have concave down. So somehow I'm going to have to go through this point and end my concavity down. I'm actually going to try to go a little lower. So go like this, right? Which I draw my concavity. And then I need to go ahead and follow concave up. So I need to go through my asymptotes and just make sure that I go to infinity and go concave up. So you guys see how we started off with our intercepts, then we went into our end behavior and our asymptotes, and then we kind of like just did the decreasing and increasing intervals to give us some shape, but then to give us like some direction and shape. But The g part, which is the concavity, which is the second derivative test, makes this function nice and smooth by making it look more like a real function than just a bunch of straight lines, because all we know that it's decreasing and increase. We don't know like at what rate it's increasing, what rate it's decreasing. And that is the whole point of the second derivative. It's about the concavity, about the smoothness of the curve, or if it's like this or like that, that's all it tells us. So now let's go ahead and do a practice problem. I know it's going to be kind of painful, but we need to just do a lot of practice on curve sketching because takes a lot of time. So let's go ahead and do a practice problem on curve sketching of a polynomial.